let us discuss this theorem. So in this theorem, we have a matrix space XD and F, capital F, is a subset of X. We have to prove that these two statements are equivalent. So that means if and only if part is there. Getting? So we assume one part first. We will assume first sentence. After that, we will prove second statement is true. After that, we will assume second statement and we will prove first statement is true. So let us start with the first part. Okay. So we assume here, assume that x minus f is open. Getting? And what we have to prove? To prove that f contains all its limit points. To prove that f contains all its limit points. That is to prove that f dash subset of f. Getting? What we have to prove? F dash. F dash means set of limit points, or we can call it as a derived set, is subset of f. This thing we have to prove. How to prove one set is subset of other? We will take one point from first set and we will prove it is in second set. So let x belongs to f dash. Okay. So that means x is a limit point of x. F. X is a limit point of f. So we have some space here. Let us use it. So x is a limit point of f. So that's why by definition, what can we write? So therefore, for every r greater than 0, what is the definition you remember? I will write bxr minus singleton x intersection f is not equal to phi. So this is in that statement number 1 we have got. By definition of limit point, we could write it. Okay. What we have to prove? To prove that, simply we have to prove that x belongs to f. Getting? Now we started with x belongs to f dash and we have to prove that x belongs to f. Then we can say f dash is subset of f. See, normally in mathematics, when we wish to prove something, okay, we most of the times we consider exactly opposite to that and we solve it. After solving, we get contradiction somewhere, then we declare our assumption is wrong. So that's why we get a given thing or given result. Getting? So our target is to prove x belongs to f. So I will assume, let if possible, x does not belongs to f. See, x does not belongs to f means what? That means x belongs to x minus f. Okay, I will draw the diagram. Small diagram I am drawing here. So this is the matrix space XD. Getting? And yeah, this is a set F. So point X does not lie in F. That means X lies in complement of F. But we know that X minus F is open. But X minus F is open. So you know the definition of open set. It is possible to draw a ball around X which entirely lies inside set X minus F. So see, therefore, there exists some radius R1 greater than 0 such that BXR1 subset of X minus F. Getting? So it is possible to find ball around X which entirely lies in a complement of F. If you remove center from a ball, then again it is a subset of X minus F. So B x r1 minus, I am removing its center, then also it is subset of x minus f. See, there is no more space to write. You can make a screenshot of it and then we will go further. So therefore, what can we write? It is subset of x minus f. So therefore, it entirely lies in diagram also you can see it entirely lies in a complement of f. So therefore, its intersection with f is empty. So therefore, bxr minus singleton x intersection f is phi since it entirely lies in its complement. So therefore, intersection with f. In diagram also you can see ball and f has a no common point. Getting? So therefore, intersection is phi. But actually we get a contradiction to equation statement number 1. because here we say the intersection is non-empty for every r greater than 0, and here r1, I supposed to write r1, yes. So for r1 we are getting intersection phi, so we get a contradiction. So I write, we get contradiction to 1. So that means our assumption is wrong. Therefore, our assumption is wrong. So what was our assumption, you remember? X does not belongs to f. That was our assumption. That is wrong. So therefore, x belongs to f. So therefore, we had started with, actually we had taken x from f dash and we proved x belongs to f. Therefore, we can simply write f dash is subset of f. Let me remove this part, it is not required now. Okay, see that means f dash means derived set of f, set of all limit points of f. Okay, and here we are saying set of all limit points of f is subset of f, that means f contains all its limit points. Therefore, f contains all its limit points. So that means we had assumed first part and we proved second part. Okay, after that, conversely we have to prove this theorem. That means I am going to assume second statement and we supposed to prove that first, that means x minus f is open. You can make a screenshot of it, after that we will go further. Let us discuss its converse part now. So conversely, we assume f contains all its limit points, contains all its limit points. Okay, so symbolically we can write that is f dash subset of f. And what we have to prove? To prove that x minus f is open. Tell me, what is a method to prove that any set is open? We take one arbitrary point and we find ball around it which entirely lies inside a set. Then we declare the set is open. Same thing I am going to do. Let x belongs to x minus f. Getting? So I have taken one arbitrary point. So see, I will show in diagram. So this is matrix space X. This is some set F we have, getting, and x minus f means complement of f. So we have taken one point x from the complement of f, getting x minus f. That means x does not belongs to f, getting x does not belongs to f. Actually, f dash is subset of f. If x does not belongs to f, then it is not a member of f dash also. I write here, but f dash is subset of f. You are getting, that means suppose something is subset of f. If x is not in f, then it cannot be in a subset of f. So therefore x does not belongs to f dash. X does not belongs to f dash means what? That means x is not a limit point of f. Getting? F dash means what? Set of limit points of f. No. So x is not a member of f dash. That means x is not a limit point of f. So see, you are familiar with the definition of limit point. For every r greater than 0, there is bxr minus singleton x intersection f is not equal to phi. Getting? So see, here it is not a limit point. That means exactly opposite definition we need to write. So what I supposed to write? So therefore, what we write for every r, now instead of that I will write there exists r greater than 0 such that bxr minus singleton x intersection f is not equal to phi, we write, but it is not a limit point. So that's why I will write it is equal to phi. So there is some ball, getting, there is some ball having center x radius r, intersection minus singleton x, and intersection f is equal to phi. That means that ball entirely lies in its complement. So therefore BXR minus singleton X subset of X minus F. Getting? See, but we had taken X from where? We had taken X from X minus, okay, sorry, X belongs to X minus F. That means BXR is subset of X minus F. That singleton X is also X in X minus F. That means both of them are in X minus F. So therefore we can write BXR subset of X minus F. So we had taken one arbitrary point and we could find ball around that point which entirely lies inside X minus F. Therefore we can declare X minus F is an open subset of XD. Therefore X minus F is open in XD. In this way we proved the first statement. Okay, so in both ways we have proved this theorem. Make a screenshot of it. After that we will stop. Thank you. Bye bye.